required by federal law to know what our employees are exposed to while at work. The only realistic means of determining dust exposure is by dust sampling. Dust sampling is also regularly conducted by MSHA inspectors. Excessive exposures identified by MSHA sampling are citable. More importantly, proper dust sampling can significantly aid in the prevention of silicosis. This video demonstrates how to correctly collect dust samples. At the end, you will understand the purpose of dust sampling, calibration procedures, the components of the sampling train, how they work, and how to collect a sample. We'll briefly look at record-keeping requirements, what to do with laboratory results, and the pitfalls of not sampling correctly. What might appear to be a rather simple procedure, unfortunately, is frequently done improperly. The result is a waste of time, money, and an inconvenience to the person being sampled. More importantly, we have lost an opportunity to find out if the miner experienced dust exposures that could adversely affect his or her health. This video points out some of the more common errors. Excessive exposures to dust can produce a lung disease called pneumoconiosis. For silica dust exposures, the specific type of pneumoconiosis is called silicosis. Silicosis is caused by the lung's retention of very small-sized particles of quartz. Larger particles are removed by the body's defense mechanisms, found in the nose and throat. Our sampling device only allows small particles to be collected. We will discuss that later. A chest X-ray is the standard silicosis diagnostic procedure for people. Unfortunately, it normally takes 15 to 20 years of excessive exposure for the disease to show up on X-rays. This is 15 to 20 years too long. By comparison, dust sampling for exposure determination is almost real time. Federal exposure rules and guidelines are developed to prevent silicosis. Therefore, by maintaining exposures below these guidelines, we feel we can prevent silicosis. That's why we sample. MSHA uses and recommends the use of NIOSH method 7500 for sampling and analysis of respirable silica-bearing dust. The purpose of the sampling system is to collect particles smaller than a certain size onto a pre-weighed filter that will be sent to a laboratory for analysis. A battery-operated pump pulls a known amount of dust-contaminated air through the filter. The dust is deposited onto the filter. There are many brands of pumps available. However, pumps must operate at a flow rate of 1.7 liters per minute for the sampling devices we use. Choose pumps that are rugged, have at least a 12-hour operating battery life, have a concealed on-off switch, and preferably show elapsed time. The first step in sampling is calibration of the sampling pump. You must know the sampling rate and sampling time to determine the volume of air that passed through the filter. Remember, for our system, the sampling rate is 1.7 liters per minute. Dust concentrations are written in terms of weight per volume of air, or milligrams of dust per cubic meter of air. The sampling rate multiplied by the sampling time equals the volume of air sampled. We are using an electronic calibrator. These are very popular and accurate devices. Connect the filter to the pump so that air is drawn through the calibration device as well as the sampling train, complete with the filter. The sampling train for calibration must include the filter because it produces resistance to air movement and to the pump. The calibration would not be accurate without the filter in place. The sampling train is all the components that must be attached to each other to accurately collect the respirable dust sample. If your calibrator is different than the one shown, just follow the instructions provided. Turn on the fully charged pump and the calibrator and generate a bubble by pressing the bubble initiator button. You do this a few times to wet the inside of the flow tube. Clear the calibrator and take 5 readings, again by depressing the initiator button, and reading the flow rate on the LCD display. The infrared device of the calibrator notes the time for a bubble to travel a given distance, and a flow rate is shown on the display screen. If the flow is below or above 1.7 liters per minute, adjust the pump flow rate, higher or lower, using the flow adjustment set screw. MSHA procedure is flow rate must be within 5% of target flow rate. Pumps should be calibrated before and checked after each sampling event. A sampling event could be a day of sampling or any continuous sampling period. These readings should be recorded on your calibration sheet. Before and after readings should be essentially the same. MSHA procedures require the post-calibration check to be within 5% of the pre-calibration. Compare your pre and post sample calibration. Are both within 5% of 1.7 liters per minute? Are both within 5% of each other? The reasons a pump does not maintain flow are many. For example, if before was 1.7 liters per minute and after was 1 liter per minute, you might question the validity of your sample. What caused the drop? Excessive dust that overwhelmed the pump or low pump battery? You should also calibrate the pump as near the sampling site elevation as practical. Consult the calibrator instructions if calibration is not performed within 1,000 feet elevation of the sampling site. You may have to do some calculations to adjust for the elevation change. The first step in collecting accurate respirable dust samples is to examine the sampling equipment. The sampling train in this case consisting of a calibrated pump, a 10 millimeter Dore-Oliver nylon cyclone, tubing, hose, breastplate, and cassette must be thoroughly examined. The hose or tubing should be clear and free of holes. The inside of the nylon cyclone must be clean, dry, and free of scratches. The O-ring, where the grit pot attaches, must be present and in good physical condition. The vortex finder should fit snugly on top of the cyclone body. The O-rings in the barrel connector must be present and in good physical condition. The next step is to remove the cassette from its protective bag. Examine the filter in the cassette housing to make sure the filter is flat and not crimped in the housing. It must be placed correctly on the cyclone for proper sampling. Let's take one apart. The reason for doing this is to demonstrate that the cassette can only be attached to the cyclone in one way. As you can see, there are 2 openings at opposite ends of the cassette. One of these openings is only for inlet air, and the other is only for air moving out of the cassette. It is essential that air from the cyclone only enter the opening designated for air entry. Some manufacturers use an arrow to designate flow direction. These particular filter cassettes have a wagon wheel design on the outlet or backside. Remember, the direction of air is from the work area through the opening in the cyclone and then into the filter cassette. Air exits through the tube that is attached to the pump. Why is orientation so important? Look at the parts. This is the filter. As you can see, it is very thin. It's resting on a backing pad. This pad helps protect the filter from damage and keeps the filter in place. The backing pad is on the outlet side of the cassette, closest to the plastic tube that goes to the pump. The filter, PVC material, is what was weighed at the laboratory and inserted in the cassette. When the cassette is returned to the laboratory, the filter will be removed and weighed again. The difference in weight relates to the amount of dust collected. So, if the orientation of the cassette within the cyclone is correct, dust will be collected on the filter. If the orientation is reversed, dust will be collected on the backing pad and the sample will be ruined. You have just wasted a bunch of time and money. Someone wore that pump 8 to 12 hours for nothing. The backing pad is not designed to collect dust, nor was it weighed prior to sampling. Always check to be sure that you have inserted the cassette correctly onto the cyclone assembly. Note that the cassette has 2 plugs or plastic covers. They are inserted into the inlet and outlet openings. They must be removed when connecting the cassette to the cyclone for sampling. They must be reinserted after sampling is completed. The purpose of the plugs is to prevent material from entering the openings when sampling is not in progress. Note that they may be different colors, red and blue for example. Do not assume that one color means inlet and the other outlet. Always examine the cassette to determine which opening is which. For our purpose, the colors mean nothing. Each cassette has a label with a series of numbers. These numbers identify the specific cassette, and the laboratory has a record of the weight of the specific filter contained within the cassette. We will discuss this further when we talk about sampling, but for now, you will use this number to describe your sampling event. Cassettes are fairly rugged, however they should be handled with some care. The cyclone is similar to a cyclone found on plant dust collectors. Its purpose is to separate particles by size. Large particles drop out into the grit pot, and particles smaller than 10 microns in size are directed to the filter that is located inside of the cassette. It is commonly thought that the particles larger than 10 microns in diameter can be rejected from the body by one means or another, so they don't make it into the deeper part of the lungs. The cyclone sorts dust by size and collects on the filter those particles of the size range that could reach our lungs. The cassette containing the small particles on the filter will be sent to the laboratory. The large particles in the grit pot are discarded. Sampling cyclones are precision-made devices, manufactured to very tight specifications. They should be handled with care and kept clean. It is important not to damage the inlet, as this could affect the size distribution of the material deposited on the filter. Flow rate was mentioned earlier, and this is extremely important. Cyclones perform their size selection at a certain flow rate. For this cyclone, the flow rate must be 1.7 liters per minute. If the flow rate is significantly higher than 1.7 liters per minute, particles actually smaller than 10 microns will be rejected to the grit pot, and you will lose particles of respirable size that should have gone to the filter. This is because the higher flow rate or velocity within the cyclone artificially imparts weight to particles, and they move to the grit pot where other larger particles go. Conversely, if the flow rate was significantly lower than 1.7 liters per minute, particles actually larger than 10 microns will be collected on the filter. Flow rate is critical. Another potential problem is the orientation of the cyclone. As you can see, the inlet of the cyclone is quite small, and it must be pointing out and away from the miner being sampled. If the opening is turned into the clothing, the sampling result will not be representative of what the person was breathing. Another ruined sample. Connecting the parts of the sampling train is straightforward. Connect the tube from the pump to the cyclone. Ensure that the tube is long enough so the pump can be attached to the belt and still permit the employee sufficient movement to do his or her work. The pump attaches to the person's belt, or you may have to provide a special belt or vest. The pump can be positioned at the front side or back, whatever is most comfortable for the person being sampled. Note that the tube is long enough to allow the person to work. The cyclone assembly is attached at the collar. This is done so that the collected sample represents the air in the person's breathing zone. It is very important that the cyclone assembly remain in the breathing zone. For example, if the cyclone was attached to the collar of a t-shirt and the work environment was very warm, sweating could stretch the collar such that the cyclone was well out of the breathing zone. The resulting sample would not be representative of the air the employee was breathing. Sometimes you have to be quite creative in attaching the cyclone. Before turning on the pump, it is imperative that you tell the employee what is happening. Explain why samples are being collected and the sampling process. Tell the employee how to reach you during the sampling period. This is very important because if anything should go wrong, such as the tube breaking or coming off of the cyclone or the pump shutting off, the problem can be remedied quickly and the sample salvaged. The employee should be told that sampling is a scientific event using precision instrumentation. The instrumentation should not be abused. The employee should also be instructed to not inadvertently bias a sample. It should not be placed, for example, on a dusty floor. The cyclone must not be turned upside down. This will result in dust separated by the cyclone being dumped onto the filter. Very minute amounts of dust entering the filter can result in an overexposure as measured by the laboratory. Turn on the fully charged pump and record the time. Let the pump run for the entire employee's work shift. You should check every few hours to see that everything is operating correctly. It is best to stay with the employee all shift, though this is not possible if you are sampling more than one worker. At the end of the shift, turn the pump off, note the time, and remove the cassette. Reinsert the two plugs into each end of the cassette. Put in the plastic bags provided and prepare for shipment to the laboratory. Then remove the pump and sampling train from the worker. A control filter should be submitted to the laboratory along with the filters used to collect particulate material. These filters are used to determine the amount of outgassed material deposited on the filter from the plastic cassette holder itself. One control filter should be submitted for each day of sampling, and that filter should be from the same lot as those filters used to collect material. The control filter should be labeled as control. The control filter should be exposed to the same time, temperature, and handling conditions as the ones that are used for sampling. The inlet and outlet plugs must not be removed. The control filter can be carried in a shirt pocket while checking the sampling process. The filter should be stored with the regular samples after sampling and sent to the laboratory along with the other filters. Cassettes are fairly rugged, however they should be handled with some care. You should pack them with noodles or other packing material when you mail them to the laboratory for analysis. This will help prevent any dust from being bounced off the filter during the shipment. Calibration setups include the filter in line, either in a calibration bottle or not. You must check the calibration of the pump and note your post-sampling calibration results. No adjustment to the flow rate may be made when making a post-calibration check. Compare your pre- and post-sample calibration. Are both within 5% of 1.7 liters per minute? Are both within 5% of each other? Sampling records must be kept to allow you to obtain and interpret laboratory results. Use a sampling form to record calibration information before and after, date and time of sampling, name of person sampled, nature of work, work area, weather conditions, filter cassette number, sample duration in minutes, activity log denoting activity of the employee by hour during the sampling period. Two pieces of information are required from the laboratory for each sample: dust concentration in milligrams per cubic meter of air and percent quartz in the sample. If you provide the laboratory with the sample period in minutes, they can provide the two pieces of information. Compare the dust concentration to the permissible exposure limit. The current MSHA permissible exposure limit in milligrams per cubic meter is determined by the formula 10 milligrams per cubic meter divided by 2 plus the percent quartz in the sample. For example, if the percent quartz in the sample was 85%, the exposure limit would be 10 milligrams per cubic meter divided by 2 plus 85, or 0.11 milligrams per cubic meter. NIOSH method 7500 has a sampling factor of plus or minus 20%. This represents the level of confidence you have in assessing whether your sample exceeded the exposure limit. Employees sampled should be informed of the laboratory results. If the result exceeded the exposure limit, you need to find out why and take corrective action. In the interim, the employee must be protected from excessive exposure, either by administrative controls, such as limiting exposure time and/or wearing appropriate respiratory protection. You can also consider imposing a lower limit on your workplace, such as the 0.05 milligram per cubic meter level recommended by the National Institute for Occupational Safety and Health, or NIOSH. Direct reading dust meters are frequently used in conjunction with filter sampling. With direct reading instruments, you do not have to send a sample to a laboratory. You see the results while the sampler is running. Direct reading meters are about the size of a pint of milk and cost about $4,000. The meter is small enough to attach to a person for a full shift sample. It can be handheld for on-the-spot readings, or it can be attached to a post or a piece of machinery. The addition of an extra battery pack can extend the sample time to 50 hours. Actual dust readings will appear on a display area in milligrams per cubic meter. The unit will continually take and record readings as often as the sampler has programmed it to. For example, it could take a sample every 30 seconds or every 30 minutes. Readings can be observed on the display panel, and the accumulated information can be downloaded to a computer in graph form back at the office. The graphs show dust concentrations and changes over time. This is valuable because, for example, unusual conditions will be depicted as definite peaks on the graph. The graph will also tell you when this occurred. These meters are terrific for detective work. You think you may have a dust leak, but can't see it. This meter will help track it down in a hurry. This particular meter is a passive device, no moving parts. Some direct reading meters also come with pumps and cyclones. They cost about $12,000 and are about the size of a small car battery. The negative factor, these meters measure all dust, not just quartz. This particular meter was designed to sample dust 10 microns in diameter and smaller. It is important to remember that this meter measures the total respirable dust. Therefore, meter readings can be compared with other meter readings in terms of relative change, but the readings should not be used as absolute standalone numbers. Also remember that these direct reading meters are not a substitute for filter sampling, and in general, direct reading results should not be compared to filter results. Again, this is because the direct meters measure all airborne dust and do not distinguish quartz. These meters are not a substitute for measuring respirable quartz, but they can be a valuable addition. As a general rule, samples should be collected first on people and later in areas of concern. Start with those persons expected to be more at risk for silica dust exposure. These would be people working in dry areas. For example, people working in job categories such as bagging, crushing, drilling, milling, screening, maintenance, and loadout. Those with less potential exposure would be dredge operators, persons working at wet plants or processes, and people working in administrative positions. Using the worst first approach, sample at least one person from each risk category. Continue sampling until eventually each person in each category has been sampled. This is important because individual work practices can have a huge impact on exposures. For example, George, cleaning a vibrating screen, could have a negligible exposure, while John, cleaning the same screen, could have an excessive exposure. The difference may be because of individual work practices. It should be apparent after the first round of sampling by category if there are high magnitude trouble spots. If so, they should be addressed right away. Subsequent sampling should be largely based on your sampling history. More attention is given to higher exposure levels and less given to those of low risk. Even low-risk exposures should be sampled, although with less frequency. The purpose is to determine if the exposures continue to be low. If controls are put into place, follow-up sampling needs to be conducted to assure the controls remain effective. A sampling plan should be developed for each calendar year. The plan will probably change each year as your database develops. Eventually, fewer samples will be collected. However, those collected will be related to relative higher exposure risk. We have discussed and demonstrated equipment and procedures for dust sampling. You should be able to calibrate a sampling pump, assemble a sampling system, attach the system to a person and collect a sample, and evaluate the laboratory results. Dust sampling is a scientific process, and it requires the cooperation of those being sampled. Good sampling techniques and appropriate follow-up on sample results and dust exposure reduction will significantly aid in the prevention of silicosis.